We'll discuss the other trade-off that we have to do. Since these are distributed systems, that means this is one system, this is another system. These two are communicating and then responding to our business requirement. And the computation is different here, the computation power is different here. This is a separate metal, this is a separate metal. So these distributed systems have their own challenges. Let's understand in detail. Compared to in-process function calls, remote calls are slower. As we have seen, we need to build the communication channel among different services. Now, if you need to do a transaction, then the latency also increases. And if there are multiple services, it again slows down the overall call. Suppose if I have to make one, two, and three and four, maybe six microservices for one use case, then to send the request and get the response or to complete this flow involves multiple services and is again a slower process, right? The latency also increases. Now if the volume of data to transfer is more, then it adds more latency to the transaction, right? So handling transactions in a distributed system gives its own challenges. Because of the network intervention, remote calls may likely to fail. That means a call from here to here may not happen. It may fail anywhere. Let's say maybe the fourth service may fail, especially with a large number of services communication and the number of failure points are increasing. That means if I have, say, 20 microservices, there are 20 points of failure, right? If there are five microservices, there are only points of failure. So the number of services increases, the number of failure points also increase. We need to monitor each of them, right? So they also drastically increase. Now, let's see the other one, observability. Observability is an important aspect of microservices. Let's see what this means. Like full stack tracing is important because when an issue arises, developers responsible for different services find it difficult to identify the root cause. Suppose this is one team, team one, and this is another team. Now there is an issue that is raised by customer. This team knows about this functionality, and this team knows about this functionality. Where it failed, team may not be able to identify it. So we need to build a capability called full stack tracing. That means we need to trace this requirement from one microservices to the other microservices, or if it involves multiple, all of the microservices tracing should be enabled. That is called observability. We need to have this kind of capability in order to respond to some issues debugging, in order to respond to some of the customer issues or end-to-end use cases, right? Then we see distributed transactions. Distributed transactions means now I have one service which will store the data, one service which will update the data. Say for example, I deposit some money in a bank, then a service need to update the record. It has to serve me a fetch the record. So there can be a insert, there can be a retrieve, there can be an update. So all these kind of different services are there. Now, in a transaction, suppose one of the service failed, then the whole transaction in other cases need to be retrieved back, right? So, if you want to address a transaction kind of scenario across multiple services, it becomes a challenge. What it can lead to is a inconsistency or consistency issues. So one service says that I have updated the database, one service says that I have not received the value, updated value, another service give some other data. So no, the state of the database keeps not consistent. There are some solutions on how we achieve eventual consistency, but however this is one of the things we need to handle in case of a microservices based systems architecture. So distributed transactions is a functionality we have to consider. So let's look at two of the solutions I briefly explained, and we will go in details when we discuss the architecture. So reduce the number of invocations. It's one obvious thing that you reduce as many services as possible using batch processing. That means instead of we invoke one service, say this is one service, this is another service. Instead of we call each time, say there is a 10 for loop, and we are calling each time this one. Instead of that, maybe we consider sending all of them as one batch and then getting as a response. If it is possible to do this, do a batch processing. It will reduce the number of calls and so the latency and so the other factors, the failure points. Instead of processing individual requests, invoke the service multiple times, we can consider to use batch invocation. Using asynchronous communication. This is also another technique. Like if I have five microservices, this one is calling, this one is calling this, it's going like this. Now the request is still waiting, right? Until it responds back, it is waiting. Instead of keeping some of the services waiting, it may fail in between. There are some scenarios where the failure is handled, retry mechanisms are created. However, instead of doing a synchronous communication, we can use an asynchronous mechanism. Using asynchronous mechanism, this will continue, and once the response comes, it will pick it up. Similarly, this will continue, and a response comes, it will pick it up. So we can identify some techniques of building the communication in an asynchronous way among the microservices. So these are two of the techniques we can think of on how we can do an architecture for microservices based application.